Let's have a look at an example of work when friction is involved. Consider a crate sitting on a horizontal flat ground. The surface is not smooth, so there will be friction between the crate and the ground if the crate slides across the ground. A force is applied to pull the crate at some angle to the horizontal surface. As soon as the force is applied, friction will react to oppose the applied force. What is the direction of this frictional force? Friction will always oppose any motion, so if the force wants to pull the crate to the right, then friction will act in the opposite direction. Let's now include the other forces acting on the crate. We have the weight of the crate acting down due to gravity, and we have the normal force pushing up from the ground. Since the applied force is at some angle to the horizontal, we can resolve it into its horizontal and vertical components. Finally, let's define our coordinate system with any vectors pointing in the right direction in the horizontal and any vectors pointing upwards in the vertical as positive. So along the horizontal axis, we have the following force equation. We have the component of the applied force to the right minus the frictional force to the left. If the horizontal component of the applied force is greater than the maximum static frictional force, remember that the crate was initially stationary, then we will have a net force that will cause the crate to slide. If F cos theta is less than the frictional force, then the crate would not move. Now let's have a look at the vertical direction. We have the vertical component of the applied force as well as the normal force pointing up, and we have the weight of the crate pointing down. The net force in the vertical must be zero since there is no movement in the vertical direction. This then gives us a normal force being equal to the weight of the crate minus the vertical component of the applied force. Going back to the horizontal direction, the frictional force is equal to the coefficient of friction multiplied by the normal force. The coefficient of friction starts as static, then changes to kinetic if the crate moves. The normal force is given by the equation on the right side of the screen. So if the crate moves and is displaced by an amount x, then the work done on the crate is the net force in the horizontal direction multiplied by the displacement, where the net force is given by the equation above. What we can see in this equation is that there is work being done by the applied force to move the crate to the right, then there is work done by friction to oppose it. Another way of looking at it is that the total work being done by the two forces along the horizontal is the work done by the horizontal component of the applied force plus the work done by friction. Since the displacement vector points to the right, but the frictional force vector points to the left, then the angle between them is 180 degrees. So the cosine of 180 degrees is -1, and work done by friction becomes negative F of Fr times x. If we now write out the formula for the frictional force, we get the following equation, where the net work done on the crate is the work done by the applied force minus the work done by friction. The two equations for work on the left side of the screen and the right side of the screen are essentially the same. Finally, as an exercise, calculate the net work done on the crate when a force of 50 newtons is applied at an angle of 30 degrees to the crate, and the crate's mass is 20 kilograms. The crate is displaced by 5 meters, and the coefficient of kinetic friction between the crate and the ground is 0.2.